Are you looking to become a network engineer of the future? The future is here, the future is now. Hey guys, Naj Kazi here. In today's video, I'm going to talk about automation. It's the hottest skill in the network industry right now, taking over the world by storm. I'm going to talk about things like SDN, or software-defined networking, and how it ties into the whole automation concept. I'm going to talk through things like Southbound interface and Northbound interface. I'm going to discuss things like Northbound APIs and Southbound APIs. We're going to discuss things like REST API. I'm going to talk through different type of SDN controllers that Cisco offers today. That includes ACI, or Application Centric Infrastructure, and SDA, or Software Defined Access. We're going to discuss differences between data center centric SDN solution versus campus centric network solution versus WAN centric SDN solution. We're going to talk through things like east-west traffic flow within the data center and north-south traffic flow within campus. This is going to be an amazing video, especially if you have not been in the network programmability and network automation realm. This is going to open your eyes to a whole world of possibilities. It's going to be a super exciting video. I am super pumped. Let's roll. Welcome to CCNA 200-301 course. Today I'm going to cover section 6, part 1. This is the network automation section of the CCNA exam blueprint. Today's video is all about SDN. Before I jump into this, keep in mind network automation is a super hot topic in the industry right now. So you're going to learn a ton and it will help you develop skills to be the next generation network engineer. Let's go. Here are the topics I plan on covering today. First, I'll provide an overview of SDN, or software-defined networking. Second, I will then provide overview of the two SDN solutions offered by Cisco. Cisco ACI, which is designed for automating data center networks, and Cisco SDA, which is designed for automating campus networks. And finally, I'll wrap it up with cloud architecture overview. Let's first discuss SDN, or software-defined network. But before we do though, I want to take a step back and articulate what a traditional network device looks like. A traditional network device has three different planes. It has a data plane, control plane, and management plane, all located on every single network device in our network. Now, what's the function of a data plane? Data plane, at the end of the day, is all about receiving traffic, processing traffic, and forwarding traffic. In some instances, we may also decide to drop traffic if you have an access control list in place, or if you have a firewall policy in place. But ultimately, the whole reason data plane exists is to facilitate traffic flow through our network. And this is where the forwarding information base comes in, for example. Then we have a control plane. Control plane is how network devices learn about each other. They get to know each other. And control plane is what allows the network devices to have end-to-end path. This is how the path is defined. Without control plane, network devices would be blind and they won't be able to forward traffic. So data plane is dependent on control plane. As a matter of fact, data plane is derived from the control plane. And finally, we have a management plane. So if you think about a brand new router, for example, out of the box, that device is not going to do anything. That router is just going to be a blank slate. In order for us to do something with that device, you're going to have to connect to it either via CLI or through a GUI, or graphical user interface. Now, if it's a home router, most likely we'll just connect to a GUI and configure it. And once it's all configured, it will allow us to connect to the internet. But in an enterprise, typically we connect via a CLI. Now, to build on this concept, like I said earlier, every single network device on our network has all three planes located on that device. Once again, the whole reason data plane exists is to forward packets To facilitate forwarding of packets, we either have IPv4 or IPv6 packets. From a control plane perspective, on our local area network or LAN, we may be using something like OSPF or ISIS as a routing protocol. But over the wide area network or WAN, we may be using BGP. This is how, once again, the end-to-end network path is built. From a management perspective, if you want to connect via CLI, we could be using a protocol like Telnet. Now, Telnet is an unsecure protocol, so do yourself a huge favor and do not ever use Telnet in your environment. It's a legacy protocol. It's still around, but you should avoid using Telnet if at all possible because it passes credentials, username, and password in clear text. Instead, you should use SSH. SSH is all encrypted end-to-end. That's another protocol we can use to remotely connect to the device via CLI. SNMP, or Simple Network Management Protocol, is used for visibility into the network. And syslog is also used to understand what's happening with the device. As different events take place, neighbors come up, neighbors go down, interface comes up, interface goes down. Every single time a system log is generated. That's what a syslog is. And through that, we gain visibility. So these are the three different planes located on every single device to be able to allow each network device to operate. Now, if we were to take a step back and look at the SDN or software-defined networking, as you can see here, as I mentioned, we have three different planes located on our device: data plane, control plane, management plane. Now, if you look closely here, you'll see the control plane is missing. What happened to our control plane? Well, typically in an SDN solution, we have an SDN controller, and what we do is we centralize the control plane onto the controller. So this way, the controller then is responsible for programming the forwarding tables of our devices. Just to provide additional context around control plane centralization, keep in mind not all SDN controllers are created equal. It depends on the vendor or the OEM that you're using. Each vendor designs their SDN controller differently. So for example, if it's OpenFlow, which is open standards-based controller, the control plane is 100% located on the controller. There's no control plane intelligence on the network endpoints. But in the case of Cisco actually uses a distributed control plane model where they do not move the control plane to the SDN controller. Okay, so I wanted you to keep in mind from a CCNA perspective, I want you to think that control plane is always located on the SDN controller. But as you go CCNP, CCIE, and beyond, and also from a real-world perspective, keep in mind that different vendors implement SDN controllers differently. Now, SDN controller's job is to centralize and automate network provisioning. So that means creating the underlay and creating the overlay. So underlay being VLANs and BGP routing and all the different other components that you may need to be able to bring up the routers and switches and firewalls and load balancers. That's what network provisioning is. And the other job of the SDN controller is to centralize and automate the network management piece. So basically, once we have an SDN controller in place, we will no longer go and touch devices individually. We'll log into the SDN controller and let the controller manage the entire network fabric instead of us having to touch each device hop by hop like we did in the past. And finally, SDN controller centralizes and automates network visibility. Now, why is that important? Well, if you think about it, in a traditional network, each device, we may be using different third-party tools, or it could be Cisco tools to be able to monitor our network, and we have a hodgepodge of syslog servers and SNMP servers, and you may be using NetFlow and NetFlow data collector, but that makes it a lot harder for us to troubleshoot because we have different tools to log into, and if something goes down, unless we receive an alert proactively, it just becomes a nightmare. When we have an SDN controller in place, that also gives us visibility into the entire fabric, 360 degree. So we have complete, deep visibility into what's going on in our network. So what I'm trying to get at here is I'm trying to give you a sense of why SDN controller was designed to begin with and what the job of the SDN controller is at the end of the day. Now, from a terminology standpoint, there's a couple of terms you want to familiarize yourself with. When it comes to SDN controller, we have what's called a Southbound interface, or SBI for short. That's the interface that's responsible for communicating with the network endpoints like the routers and switches and firewalls, the load balancers and all that. And all the devices, the endpoints, get programmed by the SDN controller through the Southbound interface. Now, how does the controller know what to push or what policy to push to the network endpoints? Well, I'm glad you asked, because that's where Northbound interface comes in. Through the Northbound interface, we can potentially log into a GUI. So for example, if it's a Cisco ACI solution, it has a nice GUI. You log into it and you go ahead and start defining different logical constructs and templates that allow us to create an underlay and overlay network, and it makes it real simple for us to be able to configure all the network devices. Now, this Cisco provided portal is an example of a native application on the SDN controller. It's an application natively written and designed by Cisco software developers to facilitate the deployment of ACI within our data center, for example. But we're not necessarily restricted to that. We could use third-party automation tools like Ansible, Chef, Puppet, or the automation tool of your choice, and you can go ahead and configure all of your network devices through these automation tools. You'll typically pick one automation tool, like Ansible, for example, and use that as a primary way of defining your playbooks to be able to configure your entire network fabric. Now, building on that terminology, we have southbound APIs versus northbound APIs. Now, before I get into the details of those APIs, well, let me first define what the term API stands for. It stands for Application Programming Interface. API is a method for one application to exchange data with another application. So let me explain. So the Southbound API allows the SDN controller to program all the network endpoints that are located south of the SDN controller through OpenFlow, which is an open standards-based SDN solution, or it could be Cisco proprietary OpFlex SDN solution used by Epic. The Southbound API could leverage CLI, things like Telnet or SSH. Like I said, Telnet is unsecure, so you should be looking into deploying SSH version 2 to be specific. Also, SNMP for network monitoring. And the Southbound API could also be leveraging netconf, which is an IETF protocol, which means it's an open standard protocol used for installing, manipulating, and deleting the configuration of network devices. It's very popular in the industry right now, and you'll learn a lot more about netconf at a CCNP, CCIE level. But here, all you need to know is that it's a very popular mechanism used for network automation today. Now, when it comes to defining what the SDN controller needs to do, that's where the Northbound API comes in. And Northbound API typically leverages RESTful API And REST stands for Representational State Transfer, or it could be using a Java API. It just depends on. The RESTful API is the most popular API because it uses HTTP verbs, and we'll talk about that in a moment. Now, speaking of REST API, let's zoom into the Northbound API component and let me give you a glimpse into how REST API works. So if you were to take an SDN controller and look into the Northbound API, let's assume in this example, I designed an application called Nodge app. And the whole purpose in life of this application is to pick a router within our network. And on that router, we can go ahead and pull information about all the active and currently operational interfaces on that router and all the configuration associated with each of those interfaces. So what we would do is in this app, the first step would be I would send HTTP GET URI request to the SDN controller. Now, before I go any further, let me first explain the HTTP verbs I was telling you about. So here are the 4 HTTP verbs that are used by the REST API: post, get, put, and delete. HTTP post means to create a URI. And URI stands for Uniform Resource Identifier. It's a fancy term for an object. So basically, HTTP post means create an object. HTTP get means read an object. HTTP put means to update an object. And HTTP delete means to delete an object. Now, as you can see, back to my example here, step 1 is HTTP get URI. So I'm saying, go to router 1 in my data center and pull all the interfaces that are live and all the configuration associated with those interfaces. So this get is basically a read request for that object. SDN controller is then going to go talk to that network device that's attached to the southbound direction. Then once it reads and gets that information, it's going to come back to my application with the HTTP GET response in a JSON data format. Now, JSON stands for JavaScript Object Notation. It's a very popular type of human readable format that is also very well adopted on a global scale today. And it basically extracts that interface configuration in such a way that it becomes human readable. And ultimately, my application will then display the results of my initial request on a web page, and it could be in an XML format. And XML stands for Extensible Markup Language. It's a web-friendly language. So once again, the whole idea of the REST API is to facilitate the automation of network programmability. Ultimately, at the end of the day, what we're trying to do is we're abstracting all the complexity away. Instead of having to memorize every single CLI command in our routers and switches and firewalls, instead, we want to use a standards-based approach whereby using HTTP, we can define our request in a human-readable format, and the SDN controller then goes ahead and translates our intent from a human-readable format into a machine-readable format, like the CLI commands, for example, and then parses all that data and returns the data back to us in a human-readable format again, so we can read what we initially requested based on that request. Now, here I'm showing an example of reading, but you get the idea. It doesn't have to be just a reading function. I could create interfaces like a loopback interface, or I can delete a loopback interface, or I can update the interface with a new IP address or an ACL or whatever have you, but you get the idea. Now, another important element that I want to bring to your attention is, so SDN, as I alluded to earlier, has a centralized control plane. Now, what are the pros and cons of distributed control plane versus a centralized control plane? Well, I'm glad you asked, because that's exactly what I'm going to show you here side by side. So distributed control plane, that's a legacy approach. It's a hop by hop approach. Centralized control plane is a more modern approach. It's a controller-based approach. Distributed control plane, there's one instance of control plane per network endpoint, whereas in a centralized model, control plane is centralized on the controller. Now, distributed control plane has a big benefit when it comes to network resiliency. It's resilient to failure, whereas the centralized control plane could potentially become a single point of failure unless we have redundant controllers configured in our network. And another big issue could be the synchronization of the state of our network or the database of our network. So let's say if we have two controllers, and if controller 1 knows about all the network endpoints in our network and controller 2 only knows about half of those devices, we have a database sync issue. And it's going to cause issues when it comes to maintaining and managing the state of our network at any given point in time. Distributed control plane, however, has some convergence challenges though. So for example, if we have 10 routers in our environment, 9 may come up okay, but one older router may have issues converging because of maybe some iOS bugs or some challenges with the hardware itself. When it comes to centralized control plane, the convergence is much better because now the control plane is located on the controller. Now, distributed control plane works fine in small environments. Typically, centralized control plane works better in large environments. Now, distributed control plane is difficult to horizontally scale because as you need more resources for the control plane, as you add more devices, your control plane gets bigger and larger. You're going to need more memory, more CPU. At some point, you're going to run out of those resources on that device, which means you're going to have to add an entirely new device. Whereas the centralized control plane is designed with horizontal scalability in mind, and all you do is you simply deploy a new instance when you need more capacity. Now, let's take a huge step back and think about why SDN is taking off now. Because that could be a question, I'm sure, that you may be thinking of at the moment. Why did SDN take off now compared to 20 years ago or 15 years ago? Even about a decade ago or so, SDN was slowly gaining traction, but over the past 5 years, SDN has taken over the world by storm. Why is that the case? It's a great question. I believe there are 3 big reasons. First, high bandwidth availability. So if you think about it, I'll give you my own personal example. About a decade ago, I had a 50 meg internet circuit at home. Today I have a 1 gig internet connection from my ISP. And it's pretty much for the same price. I don't think I'm paying a whole lot more than I did about a decade ago, but my bandwidth has increased 20-fold from 50 meg to 1 gig. Similarly, on the enterprise side of the house, both on the LAN and the WAN side, we have a lot of bandwidth-hungry applications. We want low latency. We want better quality of service. For all those things to happen, ultimately, we want to provide a great user experience. That means we need to have a lot of bandwidth available, both on the wide area networking side of the house and also on the LAN side of the house. So we have come a long way over the past many years, and especially over the past 5 years, we have come to the point where bandwidth is no longer an issue. It just comes down to how we design and architect our networks. Second of all, we're seeing an evolution of silicon chip and ASICs. So basically, if you think about like the compute capacity, we're seeing the silicon chips getting smaller and smaller in size and footprint, but their capabilities are leaps and bounds ahead compared to where we were about a decade ago. If you look at switches today, a 24-port switch, and if each port happens to be, let's say, 10 gig, that means we're going to need 240 gig worth of uplink capacity from that switch to be able to provide a non-blocking fabric And that's no longer an issue. Thanks to the advancement in silicon chip and ASICs, the throughput limitations we had on the backplane of the switches is pretty much gone. We can now do what's called non-blocking forwarding, which means we can use the full throughput of all the ports, all the way from the downlinks that are plugged into the endpoints to the uplinks. And we no longer have choking points in our network. Back in the day, we did have choking points in the network, but those choking points are almost gone for the most part, at least in the data center realm. And finally, this is the big one, is the adoption of virtualization technology like virtual machines and vMotion and container workloads, and the use of Docker and Kubernetes to manage all the container workloads. Virtualization and automation go hand in hand. And the reason for that is, so if you think about 20 years ago, if you needed a server, you would have to buy a big honking server from Dell or HP, and then you would have to wait a couple of weeks for it to arrive, and then you would install a certain application on it, and that's the only application that server ran. And then virtualization came along, which allows you to have a single physical server, but using a hypervisor, you can run multiple applications. So what that means now is you can spin up hundreds of virtual machines or even thousands of virtual machines in a matter of minutes to facilitate the connectivity for those virtual machines to be able to communicate with each other. It would be insane to think about having to go to every single network device and configuring that network device individually. That would be completely out of control. So instead, what we want to do is, as these VMs come up, we want some sort of automated way of configuring all the relevant ports, the VLANs, our routing tables, everything that we need to do to be able to facilitate the use of that virtual machine so it can communicate with other virtual machines within the environment and also to the external world if need be. So I think these are the three big reasons why SDN has taken off like there's no tomorrow. So when it comes to SDN, how is it implemented in real world? In other words, what type of solutions exist so we can leverage software-defined networking in our environment? Well, first of all, data center is the number one space in the enterprise realm where most of the technological innovation has happened over the past decade or so, especially when it comes to virtualization and automation. And the way data center SDN solutions operate is they're designed for facilitating east-west traffic flow. So what do I mean by east-west traffic flow? So if you look at this particular topology here, we got a couple of core switches, and then we got these access switches that have the different network endpoints like servers plugged into them, and on the servers you may have different VMs that are running. Within the data center, majority of the traffic flow happens to be between the virtual machine themselves. That's what's called east-west traffic flow, meaning the traffic stays within the data center, but the traffic needs to be able to communicate with other servers and virtual machines that are located within the same data center for different reasons. And I'm going to give you some of those details momentarily. Now, there are different data center SDN solutions that exist out there. One of the most popular ones that is open standards based is called OpenFlow. And what we have here is the control plane is fully centralized on the controller, and it's responsible for building the forwarding plane of all the network devices that are connected to that OpenFlow controller. Now, Cisco has its own flavor, of course. It's called ACI, or Application Centric Infrastructure. And the controller, which is at the heart of ACI, is called APIC, or Application Policy Infrastructure Controller. It's very elegantly named, and Cisco rarely names things elegantly, but here I think they did a great job because the whole idea is application centricity. And I will explain to you what that means as we continue moving along. The next big SDN solution is the campus or branch SDN solution, and this is designed for north-south traffic flow. Now let me explain what that means. So as you can see, in a typical campus network, you have a three-tier design. You got the access, you got the distribution, you got the core. as you're seeing here. So, for example, this phone right here, let's say it's a voice over IP phone. If I want to call somebody outside of my organization, traffic flow is going to go from the access, through the distribution, through the core, out to the internet. And that's what's being referred to as north-south traffic. And then when the traffic comes back, it's going to take the same path back. And this is the north-south traffic flow. As you can see, this is a very different type of traffic profile as opposed to the data center profile. Data center, a lot of traffic, east-west within the data center. Within branch, north-south. Hope that clarifies why we have different type of SDN solutions out there. Now, the first solution that Cisco had a couple of years ago, it was called APIC EM. So they took the ACI APIC and they added a keyword enterprise module or EM to make it more branch-centric. And it wasn't just a name difference, but they actually changed a lot of the functionalities within that controller to make it more campus network centric based on that 3-tier north-south traffic flow. But that was legacy. It's now called Cisco SDA or software defined access. And sometimes it's also referred to as IBN or intent-based networking. And at the heart of SD access is DNA Center or DNAC. And DNA stands for Digital Network Architecture. It's a marketing term used by Cisco for the campus controller. So DNA Center is the controller. So what APIC does in ACI is what DNA Center does in SD access. And finally, for the wide area network, now once again, if you think about a WAN design, WAN is very different than data center and campus. The whole reason WAN exists is to allow the data centers and the branch locations to talk to each other and to connect with each other. It's the connective tissue that allows the branches and the campuses and data centers to all talk to each other. That's why wide area network exists. Once again, a very different type of traffic profile. And a very different type of architecture. The big one here is the Cisco SD-WAN. It was formerly called Viptela. Viptela is a very popular SD-WAN company that Cisco acquired a couple of years ago for north of $600 million. And it brings tremendous SD-WAN capabilities into the Cisco portfolio. As of today, the Viptela solution has been 100% integrated into the Cisco portfolio. Most of the Cisco routers within their routing portfolio today are SD-WAN capable. In order to manage the wide area network solution, there are two different types of controllers you can use. You can either use the vManage controller, which was acquired through the acquisition of Viptela. So this was the original technology that Viptela had designed, which was basically a controller for managing Viptela WAN fabric. But what Cisco allows you to do is you can still use the vManage controller if you wanted to, or you can use the Cisco DNA Center controller, which also allows you to manage the WAN in addition to managing your LAN or your campus network. So it's really interesting that Cisco is kind of bringing it all together now to make it a lot simpler for users to manage their environment. And one last thought on this topic here is, keep in mind that SDN controller could be available in a virtual form factor as a virtual machine or a VM, or it could also be available as a physical appliance. Now, the most popular way of acquiring SDN controller is a physical appliance. For example, Cisco ACI and Cisco SD Access requires you to have a physical appliance. And the reason Cisco prefers you to have a physical appliance for managing your devices is because of the stringent requirements as far as the compute resources, the memory resources, the storage required for managing the entire network fabric. Physical appliance works better because Cisco kind of designed that appliance for that purpose. But as the world is increasingly becoming virtual, Cisco is seeing that trend and are slowly moving in that direction to allow customers to have a choice of just installing a VM on the hypervisor of their choice. Now, Let's quickly shift our attention to the Cisco SDN controller for the data centers called ACI. ACI stands for Application Centric Infrastructure. What it does is it gives us a two-tier leaf spine architecture. It's also called Cloth Fabric. It's named after its inventor and designer, Cloth. And by the way, interesting tidbit, this leaf spine technology was designed back in, I believe, 1950s by Cloth. It was primarily designed for telephony infrastructure within the service provider realm. If you recall the old school analog telephones, to facilitate the circuit availability, that's what the Cloth Fabric was designed. But interestingly enough, over the past few years, leaf spine architecture has taken over the world by storm. Now, before I get into the topology of leaf spine, a couple of things I want you to, from a terminology perspective, what I want you to keep in mind is, in some literature that you read, it could be called leaf spine architecture or leaf and spine architecture, or spine leaf architecture, or spine and leaf architecture, or just could be simply referred to as a two-tier network architecture, or a Cloth Fabric. All of these terms could be used interchangeably, but what I want you to understand is it all means the same thing. So do not get confused as you switch from one literature to another literature. Now, in the two-tier leaf spine architecture, at the bottom of our network, we have leaf switches. So in this example, we have 4 leaf switches, and we also have spine switches. And in this instance, we have 3 spine switches. And as you can see here, the way these switches are interconnected with each other, none of the spines are directly connected with each other, and none of the leaves are directly connected with each other. Instead, all leaf switches connect with all spines, and all spines connect with all leaves within that environment. So it's very important for you to keep in mind from a physical connectivity standpoint. It's a key concept. Another thing to keep in mind is it's non-blocking fabric. So today's data centers require a tremendous amount of horsepower. So you're looking at 40 gig, 100 gig, up to 400 gig type of fabric within our data center that is 100% non-blocking, all the way from the down ports that are connected into the different servers and different endpoints that are plugged into the leaf switches, all the way through the spine. And this model is horizontally scalable, meaning if you want to add more leaf switches, you can simply do so until the spines run out of capacity, and then what we do is we just add another spine. And by adding another spine, it just gives us the ability to add that many more leaves. Typically, you would want to check with your vendor. In this case, you would want to check Cisco documentation to see how many leaf switches are supported per spine, depending on the spine switch you're buying. That will tell you how many leaves are supported per spine. It's an important design concept for you to keep in mind. Also, it's an ECMP design, or equal cost multipath design. What that means is if there's a VM attached to leaf 1 and it wants to talk to a VM on leaf 4, all 3 links that leaf 1 has and all 3 links leaf 4 has are 100% active. There is no active passive anymore. It's all 100% active, and we can send traffic in a load balanced way across all available links at any given point in time. And it's very, very powerful. And finally, an important element to keep in mind from the ACI design perspective is the predictable nature of this design. So in the 3-tier architecture, if you guys recall, we also had sometimes what was called collapsed core, meaning the core and distribution was collapsed into a single layer, which also kind of mimicked a 2-tier architecture, but it wasn't exactly 2-tier architecture. And plus, sometimes you would have a single link between the core. Sometimes you would have like an ether channel with multiple links bundled together to facilitate traffic between the core. What that did was that created a lot of one-off snowflake type designs. When it comes to automation, we don't want any snowflake design. When it comes to automation, what we want ultimately is a predictable design that is always the same across the board, because that's what facilitates network infrastructure automation. So in this example, let me show you something really cool. So let's say there's a VM on leaf 1 that wants to talk to a VM that's attached to leaf 4. What would happen is leaf 1 would take this path and go down to leaf 4 using this path. It can also leverage other paths as well, but ultimately it doesn't matter which path it takes, it's going to be able to reach that virtual machine. So what that means is each virtual machine is 2 physical hops away. This is 1 hop right here, and this is the second hop right here, all the way from here to leaf 4, right? So 2 physical hops. Why 2 physical hops and 1 logical hop? As I explained, there are 2 physical links, but logically we could be using VXLAN overlay technology. So these VMs think as if they're directly connected with each other. In reality, they are 2 physical hops away, but logically they think they're just 1 hop away. So that's the whole idea of underlay overlay, which I will also discuss in a moment, but that's what you get with this design. Now when it comes to Cisco data center switch portfolio, you have the class of Nexus 9K switches. For leaf switches, you can buy the Nexus 9300. There's a huge variety of different options within the 9300 family that you can buy. And from the spine perspective, you have this Nexus 9500 available to you, and it comes in different form factors like the 9504, 9508, 9516. That gives you the ability to be able to have modular type chassis supporting the spine. I wanted to let you know what options are available to you when it comes to designing and architecting your network within the Cisco portfolio. Let's dig deep into the physical design aspect of ACI. So we already talked about the leaf and spine switches. Well, all the endpoints connect into leaf switches. Nothing connects directly into the spine. Now, there are some designs where certain elements may plug directly into the spine, but that's a more advanced level concept. CCNP, CCIE, and more real-world type concept. At a CCNA level, for you, keep in mind that nothing plugs into the spine. Everything plugs into the leaf when it comes to network endpoints. So that would be APIC controllers. And typically you would get a cluster of 3 APIC controllers to be able to have a quorum for high availability and redundancy. You also have bare metal servers that may be dual homed into the different leaf switches, for example. You could have different VM workloads that are running on different physical servers based on the hypervisor of your choice, ESXi, KVM, Hyper-V. You could have different type of container workloads that you may be managing through Docker or Kubernetes. You could have an external layer 3 out router, which basically connects you to a non-ACI fabric. So if you have a legacy data center that hasn't been fully migrated over to ACI, you could use the external L3 out router to be able to connect to that network. You could also have firewall, IPS, load balancers, all that, layer 4 through 7 services, also connected directly to the leaf. So as you can see, you get the idea here. Nothing plugs into the spine. The only thing that plugs into the spine are the leaf switches, the uplinks of the leaf switches. But all the endpoints plug directly into the leafs, including the APIC controller. Okay, so this is a gotcha. Some people may think, well, the APIC controller should connect to spine. No, it doesn't. APIC controller connects to the leaf. Even though everything is being done through the APIC controller, but it still connects to the leaf. That's by design. Now, let's talk through the underlay versus overlay. I'm going to keep it very simple. Everything you're looking at on your screen right now from a physical network standpoint, that's all called an underlay. Physical spine switches are underlay. Leaf switches are underlay. Bare metal servers are underlay. Routers are underlay. Firewalls are underlay. But then what becomes overlay is, for example, we may have a VXLAN tunnel between 2 VMs that are riding on top of this underlay physical infrastructure to allow them to communicate directly with each other. That happens to the VXLAN overlay that rides on top of the underlay that we built. Now, the cool thing about the overlay technology is it's regardless of how the underlay is designed, We can create different type of topologies to facilitate different type of communication. For example, using ACI, we could do vMotion between data centers, even though in between the leaf and spine switches, it's all layer 3 connectivity, but we could facilitate a layer 2. And for vMotion, we need layer 2, basically, which means we need to be on the same subnet. Using VXLAN, we can extend and we can create an end-to-end tunnel between the data centers to allow a vMotion to happen between two physically, geographically dispersed data centers, thanks to the VXLAN overlay. So these are some examples. Now, at a CCNA level, that's all you want to know. At a CCNP and beyond, we're going to go into a lot more detail into ACI. And there's a lot of different logical constructs that are part of the overlay, like tenant, bridge domain, EPGs. We'll discuss few today, but to understand at a lot deeper level, you have a lot more going on that we'll discuss at some point in the future, but I'll still give you some additional insight into ACI. Now let's look at the logical design of ACI. Like I said, there's a lot of logical constructs within ACI, and the big thing with ACI is it could be scary for people at first because it's a paradigm shift. You no longer define VLANs and subnets in a traditional way. It's a very different approach. It's an application-centric view of the world. Remember, networks exist for applications, not the other way around. So networks are basically plumbing that allow applications to ride on top of. From that perspective, Cisco completely reimagined how data centers could be automated. And that's what ACI does. And there's a term called IBN. I kind of touched on it earlier, intent-based networking. Once again, the idea is, as a human operator, we want to define the intent of what we want the network to do in a very abstracted way, in a human-readable format, and then the controller can then take our intent and convert it into technical realm, things like CLI commands and netconf configuration, to be able to go and program our network. In order to help you understand ACI logical constructs, think of a typical web application. A typical web application has a web tier. It's a 3-tier application architecture, not to be confused with a 3-tier network architecture. This is a 3-tier application architecture. So a typical web application has a web page that users connect to. That's called the web tier. Then there's an app tier. So basically anything dynamic. So for example, if I go to google.com, it presents me with the web interface. But if I go to Gmail, then all of a sudden there's dynamic elements attached to that email. And all those dynamic elements are presented to me through the app tier. And then the third one is the database tier. And this is where all the information is stored. This is, for example, where my email profile might be stored. This is where all of the email data is stored. So that's the way a typical web application is designed. Now, one additional thing to keep in mind is you have an external tier, which is basically a set of routers at the edge of our network that allow the outside users over the internet to connect to the web server. And in ACI, we have what's called a policy contract, which dictates how that traffic flow is going to look like. And the reason we have that policy contract in place is to only allow legitimate traffic and potentially segment off any attempt at hacking our network. If the external users want to connect directly to the app tier or the database tier, we're going to say exclusively as part of our external tier that we're not going to allow for that to happen. External tier can only talk to the web tier. And similarly, we can say in another policy contract that web tier can only talk to the app tier. And similarly, app tier can only talk to the database tier through another policy contract. Now, if you were to combine all of these policies and EPG at the bottom of the screen that you're seeing in front of every single tier is endpoint group. And what endpoint group or EPG is a collection of different endpoints that are part of the same group. So for example, if I have a bunch of VMs that are serving my web users that are all part of the same web page, collectively they would become part of the same EPG or endpoint group. Similarly, I will have different application VMs that are also facilitating the web functionality. They would similarly be in one endpoint group. And similarly, database. All the different instances of databases that I may have running in the background would also be part of the same EPG, and same thing goes for all the external routers that are performing the same function. Now, ultimately, what ends up happening is that those EPGs or the endpoint groups and the policies, the way those EPGs can talk to each other, this is what's defined through the policy. An application network profile is designed per application. So what you're seeing here is for a very specific web application, but you could imagine you may have dozens of different applications in our network, and for each application, you would define a different application network profile with unique policy contracts to define how the communication flow is going to look like. There's also an element of microsegmentation and security that's kind of built in. There are different approaches. We could go very deep and do things at a microsegmentation level, or we can keep things at a very high level. At CCNA, we're going to keep it at a high level. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're going to have to be a little patient because I'm working on designing an entire CCNA course. I'm going to do an official launch in the next couple of months, but until then, I'm going to keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.